Hello guys, welcome on Tesla Adventures. Today, this is a topic which is highly requested by students, and especially on their request, I am making this video on this topic. Apart from the rectilinear motion, which is the current topic which is going on. Actually, this is a topic which is rarely found in any book or somewhere else, and rarely it is being taught in coaching institutes because it is a rare concept which is being asked in JE Advance once in the history of JE Advance in 2016. We would be discussing that question also in the end of this video. But first of all, let us discuss the Coriolis acceleration. Now, in circular motion, there is a very significant and very uh, unique acceleration which is called as Coriolis acceleration, and it was firstly observed by a French military engineer, G. Coriolis. Now we'll be discussing this in detail, and I think this is the best and easiest explanation so far you would find on the internet of Coriolis acceleration. So let us suppose that there is a disk, uniform disk, which is in the state of uniform circular motion, which means that this disk is rotating in anti-clockwise sense with a constant omega. Now let us consider a point A which is at a distance of x from this point O. Okay, so let us first of all write down the accelerations of point A. You can use this coordinate system as y and x, and you can see that the acceleration of point A will be the centripetal acceleration. And the centripetal acceleration is always directed towards the center, and therefore the acceleration of point A would be towards the center like that, and it would be the centripetal acceleration, and its value would be omega square into x, r omega square, and direction would be minus I cap. Okay, you can relate this. Now, first of all, now you can see that if this disk is in the state of non-uniform circular motion, then we have considered a case in which there is a angular acceleration of the disk, which is alpha, and this is omega. You can see that alpha and omega are in the same sense, or we can say that these two are in the same direction. Therefore, omega is increasing in this case. Okay. So now you can see that there would be an acceleration which is a tangential acceleration like that, and there would be an acceleration which is centripetal acceleration. So the net acceleration of point A would be equal to minus AC I cap plus AT J cap. Okay, now you can substitute the values of AC and AT. So AC is minus omega square x I cap and AT is r alpha, which is x alpha j cap. This is the acceleration of A. You can also imagine that this point A is a part of the disk. This is a point on the disk, and this is not moving in the frame of the disk. So if we are standing on the disk at some point, then A would be or we can say that if we are standing just on A, then A would be at rest with respect to us. So I can say that this acceleration of A is in the ground frame and not in the rotating frame of disk. Now you can see that if there is a groove, and this groove is on the diameter of the disk, and this point is again a point on the groove, which is a point of the groove. So A would not be moving with respect to the point O. So again we can write down that if this disk is rotating with a uniform angular velocity of omega, then we can again write down the acceleration of A, that the acceleration of A would be towards center and it would be centripetal acceleration, which would be omega square x. Okay, so in this case we can say that the acceleration of the point A in this case would be equal to minus omega square x I cap. Now you can imagine that there is a block which is kept at this point A, and this disk is being rotated by a constant angular velocity omega. Initially this block is at, or we can say that at some instant this block is at a distance of x from O. So you can imagine this block to be moving with respect to O if we are standing on point A. So just imagine that you are a observer which has the eyes fixed on the point A, which is the point of the disk, and you are watching this block sliding over your eyes. So you would be watching that this block is moving away from the point O like that with some velocity v relative. I would be making another video which would be explaining the cause of this v relative in both rotating frame as well as in ground frame. But first of all, in this video we will be discussing only Coriolis acceleration. So this point is A, which is a rigid point, and I have my eyes fixed on this rigid point, and I am watching this block sliding over this point, over my eyes. So I would be finding this block moving in this direction away from the O with some velocity v relative. Now you can see that v relative would be like that. Okay, and in some time dt, let's suppose after this point the disk rotates by a small angle d theta in time dt, then new v relative would be like that. And you can say that the direction of v relative has changed, and v relative has not changed significantly in magnitude, but its direction has changed. So we can say that the change in v relative would be in this direction. You can apply the vector law, and this change is dv relative. And you can also observe that this change of v relative is only due to the change in its direction and not in its magnitude. So you can write down that this change is equal to this arc is equal to theta into radius, where theta is d theta and radius is v relative. So we can say that dv relative by dt would be equal to d theta by dt into v relative. Okay, and therefore we can say that this is a quantity which is having the dimension equal to the acceleration. So there is an acceleration a1 which is equal to omega into v relative. And you can also see the direction of acceleration would be in this direction only, because the direction of acceleration is always in the direction of v relative. So I can say that this a1 is equal to omega v relative into j cap. Now you can also write down this a1 in vector form, that you can write down that a1 is equal to omega cross v relative. Now you can check by Fleming's right hand screw rule. You can see that in this case this disk is rotating in anti-clockwise sense, and therefore this omega would be pointing outside this plane. Okay, so you should start your fingers from the direction of omega, which is in the outside direction of this plane, and you should point your fingers towards v relative. Okay, so you should point your finger towards omega, which is outside the plane, and you should curl the fingers towards v relative. You would be observing that the thumb is pointing towards this direction. So this is the acceleration, which is a1, and I am again reminding you the fact that this a1 is produced due to the change in the direction only of v relative. Okay, now Now let us see that what happens when this object is moving like that. See, we have already discussed then that the block would be moving in this direction with some velocity v relative, and therefore this x, which is the instantaneous distance of block from center O, would be variable. So we can see that the value of this tangential velocity, which is r omega, v tangential is equal to x omega. Now v tangential is also variable. We have assumed that omega is constant in this case. So if we differentiate v tangential, dv tangential by dt, then it would be dx by dt into omega, because we have assumed that omega is constant. Now this dx by dt is obviously v relative. So dv tangential by dt is equal to v relative into omega. Now this quantity is also acceleration. Let's suppose it is a2, and this acceleration is increasing the speed of the tangential velocity like that. Okay, because x is increasing. So you can say again that this a2 would also be in the direction of the tangential velocity like that. So a2 will be also equal to v relative into omega, and if we write down its direction, then its direction would be j cap. Now again, if I write down the vector form of a2, then it would be omega cross v relative. You can again check it by the Fleming's right hand screw rule or Maxwell's right hand screw rule, and you would be finding out that a2 is also in the direction of a1. Okay, this is a1. So I can say that acceleration is additional acceleration is observed, which is same in direction, and which is the sum of a1 and a2. Okay, so you can see that a1 and a2 are exactly same in vector form also. So I can say that this acceleration a is equal to twice of omega cross v relative, and this acceleration is called as Coriolis acceleration. Okay, so this is the Coriolis acceleration. And this Coriolis acceleration is always directed perpendicular to the v relative, and it is also linked with v relative. You should also notice the fact that if v relative is 0, if that block is not moving with respect to this disk in the groove, let us suppose that we have welded this block at the point A, so it is not free to move like that. So v relative would be 0, and therefore the Coriolis acceleration would be 0. So Coriolis acceleration is an acceleration which is observed in the rotating frame, and this acceleration is due to the fact that block or some object is moving with respect to the disk in the rotating frame. So this is the Coriolis acceleration. But now we also complete this topic by observing another acceleration. You can also see that we have seen that the Coriolis acceleration has two components, both are parallel to each other, and one component is produced due to the change in direction of v relative, and the other component of Coriolis acceleration is produced due to the change in magnitude of tangential velocity v tangential. Okay, so what if the magnitude of v relative is changing? So there would be additional acceleration a relative, which is the rate of change of the magnitude of v relative. So we can say that if this relative velocity of the block with respect to the disk is also increasing, or it is variable, then additional acceleration would be in the direction of v relative, which is also called as a relative. This is the relative acceleration of block with respect to the rotating frame or with respect to a observer which is fixed at that point A. Now, now let us see that what are the total accelerations when this disk is performing non-uniform circular motion. So there is a disk which is performing a non-uniform circular motion in which you can see that this is angular acceleration alpha, which is in the direction of omega, and a block is kept at a distance of x at this instant. So you can see that this block is free to move, so there would be some velocity v relative in this direction. So there would be Coriolis acceleration. Okay, now this block is moving in a circle at any instant, so there would be a centripetal acceleration acting towards the center. Now this block has a variable relative velocity in this direction, and the magnitude of this relative velocity is also increasing. This is being given in the question, so it is also increasing, so there would be a relative acceleration in this direction. And obviously, as this disk is in accelerating state, which is the fact that this disk is rotating with some angular acceleration alpha, so there would be a tangential acceleration which is equal to r alpha. Now if we write down let us suppose that again that point is A, which is fixed on the groove. So I can say that the absolute acceleration of the block is vector sum of acceleration of the rotating frame, or I can say the acceleration of point A, plus the acceleration of block with respect to point A. Okay, or you can also write it down like that. You can take this on this side. Okay, now this acceleration is the acceleration of rotating frame, and this acceleration is the acceleration of block with respect to rotating frame. Okay, so the acceleration of this point A is equal to the centripetal acceleration plus tangential acceleration. And this is tangential. Okay, I will write it down on this side, that the acceleration of this point A is the centripetal acceleration plus the tangential acceleration. And we can also say that centripetal acceleration is omega cross v. You can imagine that the omega is in this direction and v is tangential direction, so omega cross v is the centripetal acceleration, and the tangential acceleration is alpha cross r. You can see that alpha is outside this plane and r is like that, so tangential acceleration is alpha cross r. Okay, now the acceleration of block with respect to point A, so A of block with respect to A is equal to the Coriolis acceleration, A Coriolis, okay, plus it would be the relative acceleration, A relative. So acceleration of block with respect to A would be equal to A Coriolis is twice of omega cross V relative, which we have already discussed here. This is Coriolis acceleration, and the acceleration of this block relative to the disk would be A relative, which is in the direction of V relative. So the net acceleration of block in the ground frame will be equal to AA, which is, this is the net acceleration of block in fact. So it would be equal to AA. AA is omega cross V plus alpha cross R, and A of block with respect to A is twice of omega cross V relative plus A relative. So this is the total acceleration of this block in with respect to the ground, or we can say that it is the acceleration of the block in ground frame. Now, to explain this topic better, I would be taking a numerical which is being asked in JEE Advanced 2016, and with that numerical we would conclude this video. So now let's move on that problem. Now you can see that this is a question which is which was in JEE Advanced 2016, and this is a question based on Coriolis acceleration. Although the name Coriolis acceleration is not mentioned in this paragraph anywhere, but if we know the Coriolis acceleration, if we have the knowledge of Coriolis acceleration, then we can easily crack this question without reading this para. Okay, so the same thing we would be doing in this video or in this question, that we would not be reading this para and we would be just using the knowledge of Coriolis acceleration to solve this problem. So you can see that there is a block which is kept at a distance of r/2 initially from the center of the disk in a groove, and this disk is made to rotate with the constant angular velocity of omega in anticlockwise sense. So we have to find out the distance of this block at any time t. Now you can see that first of all this let us draw the diagram from the top view. This is the diagram from the top view, and you can see that this is the groove, and this is the block. Okay, so you can see that initially block was at a distance of r/2, but due to the centrifugal force the block moves outwards, and the force at this instant would be m omega square x. So the acceleration A relative, I can say that it would be m or omega square x. Okay, so this omega square x will be equal to dv by v dv by dx, where this v is the velocity v relative. V relative is v. Okay, so you can see that omega square x dx will be equal to v dv, and integrating both the sides. So the limit of v would be from 0 to v, and of this x would be from r/, in fact it was r/2, yes, r/2 to some r. Okay, now this is omega square x square by 2, and this is v square by 2. So limit is from 0 to v, and here limit is from r/2 to r. So this is omega square r square minus r square by 4 is equal to v square. So you can see that v is equal to omega under root of r square minus r square by 4. Okay, now you can write down v as dx by dt, So if we write down v as dx by dt, so dx by dt would be equal to omega under root of, this is x square. I can write down this radius, instantaneous radius, as x. So this is x square minus r square by 4. Okay, so dx upon under root of x square minus r square by 4 integration would be equal to omega dt integration, and limit of x would be from r by 2 to r, in fact x, and limit of time would be from 0 to t. Okay, so now in this case I'm again writing it on the next page, that integration of dx upon under root of x square minus r square by 4, limit is from r by 2 to x, and it is equal to omega t. So the integration of this function under root of dx upon under root of x square minus a square is ln or log x plus under root of x square minus r square by 4. Okay, and we'll be placing the limits, which is r by 2 to x, and this is omega t. Now you can see that this is ln or log x plus under root of x square minus r square by 4 minus, if we substitute the value of r by 2 here, then this would be 0. You can see that this would be 0 and this would be ln or log r by 2. Okay, and this is equal to omega t. Now you can you can use the formula log a minus log b is log a by b. So this is log x plus under root of x square minus r square by 4 divided by r by 2. This is omega t. Now you can see that this is x, we are taking anti-log, so x plus under root of x square plus, in fact, minus r square by 4 is equal to r by 2 e to the power omega t. Okay, and now you can see that we can just square this function to find out the value, and you can find out the value like that x square plus x square minus r square by 4, or you can just do one thing, that you can keep it here under root of x square minus r square by 4, and you can take the x at that side, so it would be this minus x, and squaring both the sides, so x square plus r square, or x square minus r square by 4 will be equal to r by 2 e to the power omega t plus, in fact, it would be square, so r square by 4 e to the power 2 omega t. Okay, plus x square minus 2x into r by 2 into e to the power omega t. Okay, so cancelling this x square with x square, you have to find out the x. So you can see that this is if we find out the x, then x into r e to the power omega t is equal to r square by 4 e to the power 2 omega t plus 1. So x is equal to r by 4, and this is e to the power omega t plus e to the power minus omega t. Okay, so this is the value of x as a function of time. So the correct answer would be option number D. You can see that. Now we have to find out the net reaction force on the disk. So to find out the net reaction force on the disk, you can see that if we again draw the diagram, and if you draw the grooves, then this is the block and this is in the horizontal plane. So one reaction would be in k cap, which is the direction pointing outwards this plane. So that reaction will be balancing out mg, and you can see that there is another reaction which is due to the, this is n dash, which is due to the Coriolis acceleration. So it would be m a Coriolis. This is Coriolis. So this direction is in j cap. So we see that the two reactions would be in k cap and j cap. So you can see that option A cannot be the answer and option B cannot be the answer, and the answer can be from C and D. So now let us find out. We can see that one reaction is mg k cap in the both options, which is also correct. Now we have to find out the Coriolis acceleration. So n dash will be equal to m a Coriolis, and n dash will be equal to m into a Coriolis is twice of v relative into omega. Okay, so n dash is 2m into v relative. Now we have already calculated this x. So v relative would be equal to dx by dt. So it would be equal to r by 4 into omega e to the power omega t minus omega e to the power minus omega t. So it is r omega by 4 e to the power omega t minus e to the power minus omega t. So we can substitute the value here, r omega by 4 r omega by 4, and if I would multiply this omega also, then it would be omega square, and it would be e to the power omega t minus e to the power minus omega t. Okay, so you can see that n dash finally would be m r omega square by 2 e to the power omega t minus e to the power minus omega t, and the direction of n dash would be in j cap. So the correct answer would be, I guess, C. Okay, so the correct answer of this one is C. So guys, this was a unique problem in JEE Advanced, and this problem made JEE Advanced 2016 so-called tougher. And obviously I agree with the students that this is a Coriolis acceleration is actually engineering mechanics concept, and you would be studying this Coriolis acceleration in BTech, and then you would be remembering me that Vaibhav sir has already taught us the Coriolis acceleration. Okay, so this concept is once asked in JEE Advanced 2016. That is why I'm including this concept in our preparation for JEE Advanced 2024. Thank you. Bye bye.